Hello friends, welcome back to our channel. In this video, we are going to discuss about different states of a Linux process and some of the important signals which are used in controlling and managing these Linux processes. In the previous video, we have already discussed about what is a Linux process, how a Linux process is created, what are the different types of Linux process, and also we have seen various commands through which we can check the status of a Linux process. So once the Linux process is created, it can be in any of different states. For example, running or runnable, a sleep state which can be interruptible, and a sleep state which cannot be interruptible, and it can also be in stop state and in zombie state as well. So now let's discuss about the basics of each of these states, and then we'll see how a Linux process will move from one state to another state based on some events and corresponding signals which will be used to transform the process from one state to another state. So let's start with running or runnable state. When a process is created, first of all, it will be in running or runnable state. So in this state, the process will occupy some of the CPU cycles so that the execution of the process by the CPU will be done. So in running state, the process is actually being executed. That means it occupies some percentage of CPU cycles, but since the CPU executes multiple processes at a time, the process need to wait for some time to get the CPU execution cycle. So in that case, the process will be in runnable state. So the difference between running state and runnable state is whether the process occupies some of the CPU cycles or if it is waiting for the CPU cycle so that the process will be executed. Both running as well as runnable states are represented with symbol R. Now when the process is running, after executing some instructions, if it needs a resource, if it has to read a file, then it has to wait until the file is opened. That means it will wait for the resource. So in that case, instead of using the CPU cycles, it will go into a state called sleep state. When corresponding file or the resource is ready, then it will move from the sleep state to the runnable or running state. While the process is waiting here for the resource, it is in interruptible state. That means we can also send a signal to wake up this process. So that is why this is called interruptible sleep state. So the process which is in interruptible sleep state can be wake up when corresponding resource is ready, and also by sending a signal to this process so that it will move from sleep state to running or runnable state. We also have another type of sleep state, that is uninterruptible sleep state, which is represented with the letter D. So here also the process which is in running or runnable state may wait for resources or some signals as well. So in that case, the process will be moved to the uninterruptible sleep state. For example, if you have an NFS mount point, if the process is reading a file from this NFS mount point, but due to some reasons, this NFS resource is busy. In that case, the process will be blocked waiting for this resource. Since this is a hardware thing, the process will move to the uninterruptible sleep state. We cannot send any signal to wake up the process from the uninterruptible sleep state to running or runnable state. This will wake up only when corresponding resource will be available or until the resource throws some error if it is unavailable. So in that case, the process will move to running or runnable state. So if the resource is available, it will execute the next instruction, and if it throws some error, in that case, it will handle the error, and accordingly it will throw some exception or error based on the functional requirement of the process. If the process is in running or runnable state, we can also stop the process by sending a SIG stop signal. So this signal will make the process which is running or runnable to move to stop state. That means we are pausing this process. We can also terminate this process by sending another signal, SIG kill, or we can continue the process by sending a SIG count signal. And if the process is running or runnable, and if the process is completed, this will send an exit function to the kernel. So in that case, initially the process will be moved to the zombie state. So this we have already seen in the previous video when we discussed about a process. In this state, that means the process is completed. From this state, the process will send another signal, SIG child, to the parent process. So if parent was already waiting for this child by using wait function, then it will clear off the process content corresponding to this zombie process from the process table. But if due to some bad coding practices, if this parent process was not waiting for this child process, then in that case, this process will remain as zombie or defunct process. That means even though the process is completed, the metadata about this process will still remain in the process table. So this means a process can be in any of these states like running or runnable state, or interruptible sleep state, and uninterruptible sleep state, and in stop state as well as zombie state. Now let's discuss about some of the important signals which will control and manage the processes which are in different states. Before discussing about the signals, let us go through the Linux commands like ps and top commands, which shows the status of the Linux processes. So this is a Linux environment with Ubuntu operating system. Let us execute the ps command, which means the process status command, with options AUX. So if we execute this, then we can see different columns about the user, PID, CPU, memory, the virtual memory represented by VSZ, and the physical RAM represented by RSS, and the terminal session and start of the process, and the time duration, and finally the command corresponding to the process. So in addition to these columns, we also can see here there is one more column, the stat column. So this stat indicates the status of the process. So here we can see the status of different processes like S, I, R, and so on. Here the status I indicates the idle thread. So this is related to the kernel threads. These are not belonging to the processes of user space. So previously these were part of uninterruptible sleep processes, but a separate status is given to these kernel threads which are waiting for the corresponding task to execute. Similarly, we can see with top command as well. In this command also we can see there is a separate column called S here. So that will show the live statuses of different processes. And here we can see the top command is being executed, which is in R state. And lot of other processes like SSHD and all, they are sleeping and they are waiting for the user commands or the resources. So now let's discuss more about the different signals and we'll see how they will control the processes within a Linux operating system. Now let us discuss about some of the important signals which are used to control the processes in Linux. In Linux we have a lot of signals. We can see what are all the available signals by using kill command. So here this is the Linux terminal session. If I execute kill-l, then it will list all the signals which are available in this operating system. So here we can see all the signals are starting with SIG, which indicates it's a signal, and each signal is represented by a name, for example SIG-hub, or it is represented with a non-zero positive integer, for example 1, 2, 3 and so on up to 64. So out of these 64 signals, we are going to cover these 7 signals in this video. But the same concepts can be applied to other signals as well. So how we send these signals to control the processes. For example, a process is running. To control this process, we can send a signal by using kill command, and also some signals can be sent by some of the actions of our keyboard. So when using kill command, either we can send kill hyphen the positive integer and the process ID, or hyphen the signal name and the process ID. Now let us start with the signal called SIGINT, or the signal with interrupt. So for example, a process is running. If we send the SIGINT signal to this process, then this process can perform some of the actions, like this may ignore the signal, or it will execute some default handler for this signal, or it can also execute some custom handler to handle this signal. Now let us see these actions with an example. Here we have an example shell script which is test.sh. We can see the content. So this will print hello, and after that it will wait for 30 seconds and then it will print hi. So when we execute this shell script, it will create a process in the foreground. So let us execute that. Now a process is created and it is running in the foreground. So here it is executing the sleep 30 command. That means it will wait for 30 seconds here. So before that, let us send the SIGINT signal, which is an interrupt to this process, by pressing Ctrl C. I am pressing Ctrl C in my keyboard. So when I pressed Ctrl C, it has sent a signal called SIGINT. So when the signal is received by the process, the default action performed by the process is the termination of the process. So that is one of the actions can be taken by any process. In addition to that, here we can see we are also running a process corresponding to bash shell in this terminal session. For example, if I press Ctrl C here, it has not done anything. That means it has just ignored the interrupt signal. Similarly, if I press Ctrl C any number of times, it will ignore the signal those many number of times. So that is the default handler for the bash shell process. So that means the action which will be performed by a corresponding process depends on what type of process we are executing. We can also catch this interrupt signal by catching the signal and by writing some custom functions. So let us change our shell script to catch the signal. So here let us try to catch SIGINT. For that we'll use a command called trap. After trap, now we need to mention the command or any function which will be executed when a particular signal is sent to this process. Here I will use some example function. and we are trying to trap the signal SIGINT. This function we need to define in this script. So let's write the function example. Here, in addition to the function, we can also specify the commands, whatever we want to execute. So for this example, we are writing a function. So in this example function, let's write some statements like, so for example, we are printing date here. Now let's save this script and let's try to execute again. The script is saved now. Let's execute the script again. The script is in execution. Now let us send the interrupt again by pressing Ctrl C. This time, whatever we have written in the example function, those should be executed as part of the interrupt handler. So let me press Ctrl C. So now when I press Ctrl C, we can see here the statements inside the example functions are executed. For example, handling signal, SIGINT, and after that the date is printed, and finally the high is printed as part of the script. This way we can write a custom handler function to catch a particular signal and perform the required execution as per the requirement. Now we have used the keyboard action for sending a signal. Now let's try to do the same by using kill command. Let's execute the test script again. So now it is executing a process. Let us verify the process ID. So this shell script is executing in a bash shell. So let's try to find corresponding bash program here. So we can see here the latest one, which is 2436. Now let us try to send the interrupt signal to this PID. So here the process ID is 2436. Let's execute this. So I think the process is already done. So let me execute again. So let's try to find the process. Now the process ID is 2442. So let us send the signal. Now we have sent the interrupt signal by using kill command to the PID 2442. So let's see what happened in another session. It caught the interrupt signal and then it has executed corresponding commands, and also it has printed date. This way we can use kill command as well to send a signal to a process. Till now we have seen the interrupt signal, which is SIGINT. Now let's go through other signals as well. So now let's discuss about SIGTERM. This signal is used to terminate the process gracefully. That means this will allow the process to complete by saving its data and also by releasing corresponding resources which are used by the process. Once that is done, then the process will be terminated by using this signal. Now let us see the example of this SIGTERM signal. So let's go to Tomcat bin directory. Now let us start a Tomcat process. So the Tomcat process is started. Let's verify the process ID. Since this is a Java application, I am searching for Java. So here we can see there is a Tomcat process with PID 2465. Now let us send the termination signal by using SIGTERM. So for that, let us use kill command again. Either we can send the signal by name, or we can also use the positive integer corresponding to SIGTERM as well. So let us use the name here. And then we need to provide the PID. So let's execute this. Now it has sent the signal. Now let us search for the process again. Now the process is terminated, but sometimes by using this signal, the process may not be terminated because of some issues with saving data or releasing the resources and so on. So in that case, to forcefully terminate a process, we'll use another signal called SIGKILL. Here, the SIGTERM is the default signal. When we use kill command, by default, the SIGTERM signal will be sent to the process. So now let's try to use SIGKILL to forcefully terminate the process. So let us execute the same Tomcat here. Again, a process is created for Tomcat. Let's check corresponding Java process. So now the PID is 2513. Now let us try to use the integer corresponding to SIGKILL. So for that we need to get the positive integer. Now let us check the positive integer corresponding to this signal by using kill-l. So here we can see for SIGKILL the integer is 9. That means we need to execute kill-9 and corresponding PID. So in this case the PID is 2513. So let's execute this. Now we can verify the process again. So the process is terminated. So this -9 or SIGKILL indicates forceful termination of the process. So now we have covered SIGTERM and also SIGKILL for termination of the process. There is one more signal which is used to terminate the process, which is SIGQUIT. So the SIGQUIT is almost similar to the SIGTERM. That means it also allows the graceful termination of the process. It also generates code dump. So what is a code dump? It is a snapshot of the process which resides in memory. That snapshot will be written to disk. This snapshot of the process is very useful in debugging the performance of the applications. For example, when we have a Java application which contains many threads, and if the Java process is very slow because of some stuck threads which depends on some resources, in that case, to identify these stuck threads in the Java process, we'll take the snapshot of the Java process. That means we'll take the core dump of Java process into disk, and then we will analyze the dump to identify which threads of the process are stuck for a particular resource, and accordingly we'll try to eliminate those dependencies within the code. In that way, the generation of core dump will help us in analyzing the snapshot of the process to eliminate the bottlenecks in the performance of the applications. So now let us see how we generate a dump by using SIGWIT. Now let us start the Catalina application for this example as well. So we have started a Tomcat application which creates a process. Let's check the process. So this is the PID of the process. Now let us send the signal SIGWIT to this process. Either we can send the signal by name or corresponding positive integer. So let's get the integer by using kill-l. Here we can see the integer number is 3 corresponding to SIGWIT. So let's execute kill-3 and the PID 2795. When we execute this, this would generate a dump which is a snapshot of the memory for this process to the Catalina output file. So let's see that. So now we have sent the signal. So let's go to the logs, and here there is a file called catalina.out file. Let's check the last lines. So here we can see it has generated corresponding thread dump. So this way we can generate corresponding dump of the process by using the signal SIGWIT. When we send this SIGWIT signal, either the process is terminated or it depends on corresponding implementation of the process. For example, in case of Java, this process may not be terminated because in the JDK implementation, it might ignore this signal and it is only used for generating the thread dump. So we can verify whether the process is still running. Here we can see the process is still running even though the dump is generated, because the implementation of this JVM did not terminate the process when we sent SIGWIT signal. So for terminating this process, we need to use forceful termination by using kill-9 2795. Now let's see the process again. Now we can see the process is terminated. The next signal is SIGHub. Generally, this signal will be used to send a signal to all the child processes of a terminal session. For example, we have a terminal session. That means we are connected to a terminal, and if we have a lot of child processes running on this terminal session, so if we try to exit this terminal session, then this signal will be sent to all the child processes which are running in the terminal session. So the processes which receive this signal, either they will be terminated or they can ignore this signal if they have started with nohub command. This we have already seen in the previous video, and also we can handle this signal in our processes based on our requirements as well. So we have already discussed more about this SIGHub and nohub in the previous video. So please go through that video to know more about this signal. And other two signals we use are SIGStop and SIGCONT. So this SIGStop will be used to stop a particular process. For example, if a process is running, then if we send this signal, then the corresponding process will be stopped upon receiving this signal. So stopped means it will be paused. So if we want to restore that process, that means if we want to make it run from paused state, then we need to send this SIGCONT signal. So let's see this now in the demo. So for this, let's take the example shell script which is test.sh. So let us try to execute this script. So now it is running and then it is executing the sleep command. Let's try to get the PID of the process. So this is the PID 2865. Let us send the signal to stop this process. So now let us see here in the terminal session 1. Now we can see the process is stopped. Now if we want to make this process running again, we can use SIGCONT signal. Now let us send that signal. Now let us see here. Now we can see the process is started again. So this way we can use the two signals SIGStop and SIGCONT to pause the process and to run the process from stop state respectively. Now we have learned about 7 important signals. Out of these 7 signals, the SIGKILL and the SIGStop, for these two signals we cannot trap them. That means when we send these signals, the default actions would be taken by the processes. So we cannot customize the actions when these signals are received. For other signals, we can implement our custom routines based on the requirements. So that we have already seen how we can write the custom function for interrupt signal. So we can apply the similar concepts to other signals as well. So in this video, we have seen different states of a process. We also have seen the important signals, and we have seen how to control the processes by using these signals. I hope this video helps. If you like the content, please like, share and subscribe. Thanks a lot for watching.